Okay, welcome back student. In the last class we learned how to write a function in terms of Fourier series, and today, as I mentioned in my last class, that we will learn few identities, few theorems which is important and you should know. So, let us start with something called Parseval's Parseval's theorem. No, it is first Parseval's relation. First, let us write first Parseval relation. So, it is a straightforward relation. If a function, let me write a function in terms of Fourier series. Fine. So, I write a function in terms of Fourier series where you should always remember that these coefficients are very important. We are more enthusiastic, should be more enthusiastic to find out what is the coefficient. Here the Parseval relations suggest that if I try to find out the average of this function, say this function is in the limit minus pi to pi as usual. The Parseval relation suggests that if I want to find out the average of this function, there should be some relationship between average of this function and this coefficient that we need to find out. So, what is average of, basically I try to find out average of this quantity, because this function may be real, may be complex. So, average of this quantity, which is nothing but the norm of this function, norm square rather, then it should be written in this form. This is the way we write average of a function. This function, because in this case we have taken the norm square of this function with a limit minus pi to pi, and this is the square of these things. So, this is the original function multiplied by dx. So, now if I want to find out what is the value of this with this limit, then readily I can understand what should be the value of this average. So, the question is, what is this? This thing is nothing but a0 by 2 plus a n plus square of that, straightforward square, because I am for the time being I am considering this is the coefficients are real to make the life simple. But even if it is not real, if it is complex, if you take the mod, the procedure will remain same, the way we will do is same. Now, if I make the square of this quantity, it should be something like a plus b plus c. It is, if you consider like this, then you will have something, some term square this is the first part, the square term, because if you start multiplying, you will getting this square term, this into this, this into this, this into, there are infinite number of terms you should mind. But apart from that, there are other terms which are cross terms. I should write it cross. Why I write it cross terms? Because all the terms that will be multiplied by this or this or this. Self multiplication term will be this and cross term will be there. So, why this cross term? I write this cross term here, because this cross term the contribution of this cost term eventually going to be 0, and that is the most important part in this particular formalism. Why it is 0? Because I am taking the limit minus pi to pi, which is nothing but the inner product of whatever the basis function I am using. So, if I write that, then if I put this here, and if you just try to appreciate this case, okay, let me write it from here. So, now I want to integrate this minus pi to pi and dx. In the right hand side also I need to do the thing minus pi to pi dx, because I am writing this part only, 1 by 2 pi I am not considering for the time being. I am doing these things, and I will integrate this minus pi to pi whole this term with a third bracket dx. Now, I can separate out this contribution and the rest of the contribution which I write cross. So, let me write this term minus pi to pi, all this cross term as something phi 1, this term as something by definition. Okay, let me do it here. So, I will finally have, so this quantity 1 by 2 pi minus pi to pi fx dx, mod square dx rather, it is something like 1 by 2 pi this quantity. So, minus pi to pi a0 square by 4 plus summation of a n square sin square nx plus summation of bm m cos square mx. This is the first part with dx plus the cross term with the integration this. So, I should write this as the cross term phi I phi j with integration say I j. So, this phi I phi j is nothing but all the cross terms of the set of these things. It will be sin x multiplied by cos x, it will be 1 multiplied by cos x, it will be cos x sin x multiplied by 1, all the thing. So, this thing is nothing but with I not equal to, since it is a cross term, it is I not equal to 0. So, this term will be 0, all the cross term. Why? Because they are orthogonal to each other, and we know that when the functions are orthogonal to each other, the inner product will going to vanish, and this is the summation of the inner product of the cross term. So, that means this term will going to vanish. So, only leftover term we have is these square things, and now we need to evaluate this term, this thing term by term. So, that means what is my first term? 1 by 2 pi will be there, a square by 4 multiplied by 2 pi. This is my first term. What is my second term? Second term is 1 by 2 pi summation over n a n, and I put this integration minus pi to pi sin square nx here with dx. Separate it out, the integral sign is over a n, I take it outside and push this integration inside, so that I can evaluate this quantity, plus 1 by 2 pi into summation of m bm cos s square mx dx with the integration minus pi to pi. The first term I have already evaluated, so it will be simply a0 square by 4. Second term is 1 by 2 pi summation over n a n, and I need to evaluate this term, and I believe you have already an idea how to evaluate this term. This is a simple thing, and we have already done in the previous class. Take half of that, then 2 of sine square I can divide 2 of sine square as 1 minus cos 2 n x with a half. I replace this function here, and when you integrate this function, this cos will remain sine. When this is sine, 2 pi minus pi 2 pi limit, this term will going to vanish, and only you have this thing and half. So, you will finally the integration of these things will be simply half of 2 pi. What about the last term? Exactly the same thing, integration of this quantity, I will replace this as 1 plus cos of 2 m x. Okay, here maybe I write 1 minus cos of n x, but it will be cos of 2 n x with a half term. This term is also represented by this half, but this minus sign will be plus because this is a cos square. So, straightforward thing, and when you integrate, this cos will remain sine. When it will be sine, then if you put the limit, it will going to vanish, only this contribution will be there, and as a result we will have the same thing. Because this integration I have done earlier, so I am not meticulously doing all the integration, it will take much time, and I believe it is not a very hard thing to understand. So, it is something like this, square is missing here. Okay. So, this is the final average value I am looking for, this is the average value I am getting. So, what value I am getting? So, average is half of a0 by 2 square plus summation of a n square plus b m square. So, average value is related to the coefficient, and if the average value is related to the coefficient, it will be something like that. So, if I have the value of coefficient, if I square and add and make divided by 2, the value I am getting is basically the average of this function. So, this relation is called the Parseval relation. Okay. Now, we need to go to another important thing. Before that, we need to find out what is the meaning of this Fourier transform. So, let us one important thing. Fourier transform. So far we are dealing with Fourier series, now we are saying something Fourier transform. This word is not a very new thing, new word to you, but we like to, in this class I like to show you how from the Fourier series you can end up with the Fourier transform and what is the condition for that. So, let us write in this way. So, f x is something a0 by 2 plus summation of a n sine of n x pi by L. I write it because of some, because my function here is defined minus L to L. I am writing this notation because this notation you have already, I have already introduced. It is the same thing, but when the limit is not in pi but L, then I need to rescale these things. So, I rescale that. That is the only difference between the previous thing and these things. Okay. So, now I like to write these things in a different way, and you can readily understand what is the thing. So, I write this as the whole, say Cn e to the power of I n pi x by L. I write this thing in this way with n is equal to minus infinity to infinity. So, you can understand quite easily why these things and these things are same, because I just replace this sine and cosine. You know, e to the power I theta is equal to cos theta plus I sin theta, and e to the power of minus I theta is cos theta minus I sin theta. From these two expression, I can always write e to the power I theta into the power minus I theta in terms of sine and cos. So, sin theta is e to the power I theta minus e to the power of minus I theta divided by 2I. In a similar way, cos theta is e to the power I theta plus e to the power of minus I theta divided by 2. What I do is just replace this sine and cosine in terms of e to the power I theta and e to the power minus I theta. After doing that, I can take, if I do, it will look like something like this. Sin theta I will replace just 1. Let us put it, let us call this as the theta. So, it is theta minus I theta, one series, and another series is Bn or Bm by 2 e to the power I theta plus e to the power minus I theta. Now, what we will do that, please check one thing, that this n and m is I just distinguish, but I can write the entire thing in terms of single variable, single Dami index. So, if I replace this m into n, there is no problem at all, there is no problem at all. Then I can always write this theta and this also theta, and this is Bn. So, when I write this thing, entire thing, then what I can do, I can take this e to the power theta one side, say something like this, a n by 2I plus b n by 2 multiplied by e to the power of I theta, one term. Another term is a n minus of a n by 2I plus b n of 2 e to the power of minus I theta, right, with n n. So, I can write this e to the power I theta e to the power minus I theta a 0 by 2 in this term, whatever the expression is giving to me, which is straightforward. Then I can accumulate everything in a single summation, and this single summation is this, by putting n tends to minus infinity. Why? Because the positive integer is there, also this is minus sign. So, negative integer I can introduce and this limit will going to change. So, essentially I can write these things in terms of this also. Okay. I show explicitly how you can do that. So, I believe you will understand that it can be quite doable. So, next thing is fx is this quantity. Now, I can correlate these things to my original expression of orthogonal functions or basis. So, these functions is written in this way. I can correlate these things to this. So, that means this is nothing but this set of functions. Next, what we will do? Next, I will try to find out what is my Cn. Cn is how much? I know how to find out Cn. It is phi n f divided by mod of phi n square. This is the Fourier coefficient. We have wrote these things several times. We wrote these things several times. So, we have shown this several times. So, what is the phi n mod square here? It is 1 it is integration of minus L to L, integration minus L to L. The function is this multiplied by this, so complex conjugate of this, so it will be just 1, right? It will be just 1 because I am multiplying the same function with the same function with a complex conjugate. So this complex conjugate will be this function will be multiplied by the complex conjugate, so this plus sign will be minus sign, and when you multiply it you will get 1. So you will have 2L for that. So this quantity is 2L. What about the other thing? Phi n f of x, by definition it should be minus L to L f of x multiplied by phi n, so it will be e to the power of minus I n pi x by L dx. This up to this is fine. So now I should write the entire thing here. So f x, so let me write it here. So f x is summation of n tends to minus infinity to infinity. C n I figure out, C n is 1 by 2L integration minus L to L f x e to the power of minus I n pi x by L, and then dx, and of over that I will have 1 e to the power I term, e to the power I n pi x divided by L. So this is my entire term, right? So now I will put something interesting here. May not be required that. So let us put k with a subscript n is equal to n pi by L. So this quantity n pi by L can be represented by k n this. So what should be my delta k? Delta k, so n is a k is a discrete quantity, because n is integer 1, 2, 3, 4, minus 1, minus 2, minus 3, minus 4 and so on. So if I want to find out what is my delta k, it should be k n plus 1 minus k n, this quantity. It is nothing but pi by L, pi by L. So k is replaced by pi by L. So I can replace 1 by 2L from this expression. I can replace 1 by 2L as delta k by 2 pi. Now I rewrite this expression once again. F of x is equal to 1 summation of n, which is minus infinity to infinity, 1 by 2L. I will replace this as delta k by 2 pi. Then I integrate minus L to L f of x e to the power I. This quantity I replace k n x with a negative sign, and rest of the term with dx, and rest of the term is e to the power of I k n x, this quantity. Well, up to this I will have something which is discrete, because my summation is also from minus this to this. So this summation is a discrete summation. But now one important thing I will do, that is I will change these things. So what I will do, that I will go L tends to infinity. So I will extend my limit to infinity. When I extend L tends to infinity, what happened, that my delta k will be tends to 0. That means when I, because from this relation L tends to infinity, delta k tends to 0, and as a result this discrete n will be gradually become a continuous limit, because I am taking with the condition that my small delta k, which is the difference between these two, is pi by L, and now I extend my L tends to infinity, that means huge distance, so that all the small segment of k, delta k, which is depend on n, is become 0. So, this discrete n tends to 0. So, that means I will now have a relationship in a modified form, and this modified form is something like, I can write it as this 2 pi, I write this 2 pi into two different 2 pi, then minus infinity to infinity, because already the limit is goes to infinity. Only thing is that n is now not become a discrete function, it is something f of x 1 by root over of 2 pi, L limit is also minus infinity to infinity. So, I will put this integration also, and I push this integration by putting L tends to infinity and minus infinity. So, here these things e to the power of minus I, since the discretization of k goes away. So, I can now write k as my continuous k with dx. Over that I will have e to the power of I kx and dk. So, please note that this 1 by 2 pi I divided 1 over root pi and 1 over root pi. 1 over root pi I will take outside, another I will take inside. Fx are already there, e to the power I is replaced by e to the power I kx, because the discretization of k is now removed. So, this summation sign which is over discrete thing is now will be replaced by integration. So, I changed to add the integration sign. So, that is why this dk is now not a discrete dk delta k, rather it is a dk. I put it here dk, so that this integration will go minus infinity to infinity, and I will have this 2 term here. So, I will put the here. So, now I should write this term, say I write this term f of tilde of k. If I write this readily, you can have the form of Fourier transformation. Let me write finally what I am getting. I am getting f of x is equal to 1 by root over of 2 pi integration minus infinity to infinity f tilde k e to the power of I kx dk, where f tilde of k is 1 by root over of 2 pi minus infinity to infinity f of x by definition e to the power of minus I kx dx. So, with this we landed up to a relationship between f x and f tilde k, which are Fourier transform conjugate to each other. So, f x I can write in this way, the Fourier conjugate f tilde k I can write in also this way. So, now this treatment, from this treatment you can understand that this Fourier transform concept can be achieved by your known concept, which is the Fourier series, and when you discretize, when you extend the limit up to infinity, then this discrete thing will be go away and you will have a continuous variation, and under this continuous variation you can have a relationship between a function and its Fourier components, which is nothing but the coefficient of when we are doing these things over the normal summation. So, if you know what is the my f x, you can readily know what will be my f tilde k. If you know what is my f tilde k, you can also find out what is your functional form f x. So, with that note I would like to conclude here. So, today we have learned a very important thing, the relationship between the average function which we call the Parseval's relation, and also we learn how to make a Fourier transform from Fourier series. So, Fourier series and Fourier transforms are not a very apart thing, but they are somehow related when the continuous limit. So, under continuous limit you know how to do that. So, in the next class I will also like to show few important theorems like Parseval's theorem, Parseval's relations. Parseval theorems today I already show, and another important thing, say autocorrelation. What is the meaning of autocorrelation regarding this Fourier? This is the small things, but I believe you should know at least what is the meaning of that and how it is related to this treatment. And then we will go to another topic which is called the polynomial space, or we will deal with something polynomial. After that we will finish our vector linear vector space course, and then we will go to the next course which is complex analysis, but we will take another couple of class to finish that. With this note let us conclude here. So, see you in the next class.